Hi, everyone. Thank you. I guess I want to thank the organizer for inviting me. And actually, it's not NISQ-Era, it's tilde NISQ-Era, and in emphasis on the tilde. And yes, I want to tell you about an algorithm that my colleague Amir Kalev and I have developed and was recently published. And what I want to convince you of, and of course, interrupt as much as you like, I want to convince you that we can get a simulation algorithm that is NISQ-ish and has near optimal precision scaling. That's the idea. So the outline is probably something you already familiar. I mean, tell you about the general scope of Hamiltonian simulation in the NISQ-Era. And then I'll present the method, which I'm sure some of you have heard about from me many times even, maybe. And then I'll present the algorithm. So what is the status, as I see it, of Hamiltonian simulation in the NISQ-Era? So we have many algorithms, of course, that do Hamiltonian simulation. Now, I'll define it exactly, but I know that all of you know what Hamiltonian simulation is, essentially evolving state under Hamiltonian with time. And most approaches nowadays are really asymptotically optimal, like every other paper tells us that we have optimal scaling and so on, qubitization and LCU and so on and so forth. But if you look at what people are doing, like what people are putting on IBM, for example, on the IBM chips, you'll see that none of them actually implements any of those asymptotically optimal algorithms. They actually use Trotter-type methods. And the reason is that while those algorithms are asymptotically optimal, they have ancillas and extra stuff that goes away when you go to infinite large scale. But when you go and try to do that on a very small chip, then you find that it's not going to work. The depth of the circuit is just too much for a 20 qubit, 100 qubit machine. And so we were wondering whether there is a need to, I guess, have an algorithm that is both asymptotically optimal and also we can put on a NISQ device. That's the idea. So what is Hamiltonian simulation? Essentially, somebody gives me a Hamiltonian, and they give me a time t, and they prepare a state. And what we want to know is actually the wave function after time t evolved under the Hamiltonian. Of course, we normally don't want actually the wave function. We want some properties of the wave function. But let's say that what we need is the actual wave function, and we can do measurements at a later time. And if we can build, the Hamiltonian in a lab in some way, then we can actually carry out the experiment. It could be, a molecule. It could be a lattice. It could be whatever. But in most cases, experiments are very difficult to carry out, as more than half of us we learned the hard way. Very difficult. And so what quantum computers give us is actually a way to simulate the evolution of a wave function under a Hamiltonian for a time t. So the idea is to build a quantum circuit that approximates the unitary evolution. I'm assuming for this talk that the Hamiltonian is time independent, but in fact, those results generalized, the results that I'm talking about can be generalized to time-dependent Hamiltonians. The mathematics is more complicated, but it can still be done. So let's say that the Hamiltonian is time independent, and so the unitary time evolution is simply e to the minus IHT. And we want to write a circuit that approximates this unitary. And the question is, of course, what's the cost of that? What is the computational complexity of this procedure. This is called Hamiltonian simulation, as probably you all know already. And the first algorithm that came, I guess, to fruition, or at least the theory, was by Seth Lloyd in 1996, where he actually took his Q from actually the classical algorithm of quantum Monte Carlo, where they did what we call Trotterization. And the idea was to take the unitary e to the minus IHT, write it as a product of short-time evolutions, and just do each and every one of them, and essentially have a series of circuits, each of them evolving for a short time. And why short time? Because at short time, this exponent, because the norm of this operator is small, then the exponent is roughly the identity, and because it's roughly the identity, you can use certain tricks that where, for example, if you write the Hamiltonian as a sum of two non-commuting, but let's say we have A is in the Z basis and B is in the X basis, then you can roughly approximate e to the I minus I, the Hamiltonian delta t, as a product of e to the minus I A delta t, and then again, another one with B. And there's some error, but if delta t is small, then the error is O of delta t squared. I know probably everybody here is familiar with that. And then you can evolve this, because it's diagonal, we know how to do it. And B, if it's in the X basis, then you just switch bases by some unitary that takes you from Z to X, and this becomes diagonal, and so on and so forth. And then you just take a bunch of them and do that. Except that the problem is that if you calculate the dependence of the error, then there are these annoying Trotter errors that are proportional to delta t squared. Today we have other methods, delta t to another power, but it's still polynomial in delta t. So in fact, the dependence of the target precision is a polynomial in epsilon, the error, the tolerance. And so well, when Lloyd came up with it, it was optimal. It was the only one. It was a breakthrough, in fact. Today, I mean, when we read papers about Hamiltonian simulations done on actual quantum hardware, I think all of them are doing Trotter, essentially, one version or another. A few years ago, there was a to me, it was a groundbreaking paper by Berry et al., Childs, and I think Soma and others, where they took the idea one, I guess, level up in some sense. And interestingly, for those of us who come from condensed matter, like myself, Lloyd took it from the idea of Trotterization from first generation quantum Monte Carlo, and Berry et al. Took their idea from kind of second generation quantum Monte Carlo. Probably they didn't know that. The fact that I'll tell you a little bit what they did, and then maybe I'll connect it a little bit to quantum Monte Carlo, which is a classical algorithm that condensed matter physicists use to study quantum many-body systems. But they said, take the unitary, still write it as a product of short-time evolutions, but now take the Hamiltonian and write it as a linear combination of unitaries. These unitaries can be Pauli strings, for example. And once you have the Hamiltonian written as a linear combination of unitaries, you can take the unitary time evolution operator and just Taylor expand the exponent. And if you do that, and you just expand everything, you end up with products of, because you have h squared, h cubed, and so on. So you end up with still a sum of products of constants times products of, say, Pauli strings or unitaries. And of course, products of constants are constants, and products of unitaries are unitaries. And so they were able to write the time evolution operator, at least the short time evolution operator, as a linear combination of unitaries. And actually the breakthrough was that is this LCU lemma that, again, I'm sure that many of us know and love at this time. And I probably won't have time to talk about the lemma. I have a couple of slides about that, but we'll see how much time I have. But the LCU lemma, linear combination of unitaries lemma, tells us that if we have a unitary, it could be very complicated, but we can write it as a linear combination of simpler unitaries, then there is a technique, the LCU technique, that tells you exactly what to do to simulate up to some error the total unitary. All you need to know is to prepare a state with those square root of these constants, linear superposition of these alphas, and then these unitaries in a controlled way, controlled version of these unitaries. And if you do it for each u delta t and you stack them up one by one, you actually get the full unitary and you are home free. The amazing thing is that asymptotically, the dependence on epsilon on the error is actually exponentially better than the Trotterization, Lloyd's Trotterization algorithm. But the problem is that it requires ancillary qubits. And not a lot, but when we go and do, try to put that on a NISQ device, then it becomes a problem, even though asymptotically the error dependence is really exponentially better. Another thing that one can point at, I guess, is that the LCU requires the decomposition of the Hamiltonian to very many terms, because you need to write it as a linear combination of unitaries, and think of like a Fermi-Hubbard model or whatnot. You need to write it to do the Jordan-Wigner or whatnot, and then write everything as a linear combination of Pauli strings, because the Hamiltonian is Hermitian, but you need to write it as a linear combination of unitaries. So usually you write it as a linear combination of Pauli strings, and if you count them, there are many of them. So that's a problem, and the number of them actually, I guess, permeates to the complexity of the algorithm. And so while in principle, this is all good and fine, in reality, we are not actually using it. And there are a couple of other tiny things that one can really quibble about, which is the fact that, for example, if somebody gives you a diagonal Hamiltonian and you did the LCU, write it as a linear combination of unitaries and so on, then it would cost you quite a bit. But we know that if we want to evolve under diagonal Hamiltonians, this is very simple because these are just phases. So somehow the LCU method doesn't really, I guess, take advantage of all the properties of the Hamiltonian. This is not to say that this is not this is a bad method. It's a great method. But we were asking ourselves, I mean, given that, and one other thing which many people present as the actual problem of why not doing it on NISQ is because, as I mentioned, the unitaries have to be controlled, and if you have very long Pauli strings, then controlling or writing a unitary that is controlled on various unitaries, essentially you have a line that tells you which unitary to use, and it's controlling which unitary you apply. This is called the select. It's very complicated because there are many unitaries and they are very different, and usually it's a problem. And again, I know that some of you probably have tried it and decided it's a beautiful algorithm, but I can't really use it. It doesn't give us good, essentially on a NISQ device, it doesn't produce sensible results. It actually gives us noise, but maybe, of course, in a year from now, it's not going to be the case. I don't know. But that's the situation right now. All right. So what we were kind of set out to do is we asked ourselves, can we devise an algorithm that is both asymptotically optimal, like the LCU Taylor stuff, and is still NISQ friendly? And this is what we came up with. And again, this is NISQ-ish friendly, as I mentioned, and you'll see what I mean. But maybe I would still call it NISQ friendly, but of course, again, it's a judgment call. Anyway, I want to present to you this new algorithm that is based on what we call the PMR methods, permutation matrix representation method, that essentially tells us that if you want to do Hamiltonian simulation, don't write the Hamiltonian as a linear combination of Pauli strings, do something else, okay? And that something else is, once you pick a basis for your Hamiltonian, you want to present it in one way. I mean, maybe the Pauli Z's are your computational basis states. So you will call it the diagonal, the basis states, we'll call them the computational basis. We just choose a basis. And then after we choose a basis, we write the Hamiltonian as a sum of what they call monomial operators. Monomial operators are also called generalized permutation operators. And what it means, essentially, for those of you, again, it's probably mathematicians may be familiar with these terms, but people from our neck of the woods, not so much. It's essentially, if you write the Hamiltonian as a sum of monomial operators, essentially it means that you want to write it as a sum of products of diagonals times permutations. So this is just a way to represent it. So let's say that this is the Hamiltonian. It's a 4x4 matrix. The diagonal times a permutation essentially means that it's kind of a permutation, meaning that it has one non-zero entry per row and per column, but it's not permutation, it's permutation up to a constant. So I wrote it like that. So for example, this matrix can be written as this generalized permutation plus this plus this one. They all have one row and one column. What they do essentially when they act on a computational basis state, they just permute it times a constant maybe. But that's what they do. That's why they call them generalized permutations. But you can think of them as diagonals times actual permutations. So diagonals are just diagonal matrices in this basis, times a permutation, an operator that just permutes the basis states. So it's just 1 and zeros. So one of them will always be, the identity. That's the trivial permutation. Others will be other things. I'll give you more examples. But essentially, I can show you that you can always do that, and it's very easy to do that for any physical Hamiltonian. I can really promise you that. In fact, if we talk about qubits, and qubits are actually spin-half particles, so if we stick to these being the diagonal version, so for example, the diagonals times the permutations are pretty simple. So one of the permutations, P0, is just the identity. And so D0 is just the diagonal part of the Hamiltonian. So it's just all the Z's, ZZ plus ZZZ plus identity. And so these are all the Z parts are shoved into D0. All the other things, what are the permutations in the spin-half framework? The permutations are, in fact, just the Pauli X strings, right? Because an X operator, when it acts on a computational basis state, it just flips the state, so it permutes it. So if you want to think about it like that, this is a much more general theory, but for all intents and purposes, our permutations are just all those x and xx that appear in the Hamiltonian. And for example, if we have a Pauli y in the Hamiltonian, then a Pauli y is just an x times z times I, but it means that even a y operator is a x, a permutation, times a diagonal, a z. So it's very easy. For example, in xy model, if you have xx plus yy, you write it as xx times identity minus zz. And so the point is that it's very easy to write the Hamiltonian as a linear combination of d's and p's, diagonals and permutations. And we're singling out the d0, which is just the classical part or the z part of the Hamiltonian. So it's very standard stuff. I noticed that I was promised questions, and that is all. Okay, let's start with you, and then okay. Yes.
So when you say it's very easy to find this diagonal matrix DJ and this permutation operators PJ, you mean that we have some computational schemes to compute these operators?
I say that, but I can even tell you more. Give me any spin-half Hamiltonian that is written as a linear combination of Pauli strings. So just find those x's. You'll have an x term. This will be one of the permutations. If you have a zz term, this will belong to d0. If you have a yy, then you write it as xx times zz. So it's very straightforward. So you can usually, for any physical Hamiltonian, you can simply do that. So for any physical Hamiltonian, we can prove that it's very trivial to do. Okay?
So then, if you decompose the Hamiltonians in that way, then in fact, then for a lot of these diagonal operators DJ, it will just be a number. So
yes, it could be a number. So we'll say that it's a number times identity. Okay? But that's what it means. Okay? Yes, please.
Yeah, these DJs probably have to have some kind of structure, right? Or else you're going to be loading a lot of information into your quantum computer.
So it's true, yes. So for example, I could have a situation where I have sum of zi xj or zi, I guess, yeah, alpha ij zi xj, and so essentially we'll have a bunch of terms that belong to just, or I should write it as sum of j, sum of I, alpha ij zj, or xj, so it's sum over I. Yes, so it's true. It will be a complicated, generally speaking, it's going to be a non-local diagonal. Yes.
But I assume you picked your Hamiltonian in such a way that these.
Oh no, I'm okay with that. That's fine. That's fine. Yeah, that's not going to. It's okay. It's very easy to calculate these values. I'm only going to calculate them on computational basis state, so they are very efficient to calculate. Very efficient.
They might be efficient to calculate, but like loading them into the computer might be expensive.
So I'll show you that's a good question, but I'll show you that we don't actually load them. We don't need to load them.
Very nice. Okay. Looking forward to it.
Yes, Kevin.
So if I multiply out the DJs times the PJs, is that not a linear combination of unitaries or no?
No. This times that or this whole thing, it's not. Each term is, but it's a sum of terms, so it's not. A sum of unitaries is not a unitary. So generally speaking, a generalized permutation operator is not a unitary. Okay? Or a constant times a unitary. All right? It has much more structure. And also I wanted to bring it up later, it's much more compact form because this whole thing is a single PMR term, but still, if you wrote it in LCU, language, then it would be many, many terms, O of n terms rather than O of one term. So it's a much more compact representation. Okay? All right, okay. So what we keep doing, I guess the way we carry on is do exactly Taylor expansion in the sense that we Taylor expand the exponential, sum over minus I delta t. I'm assuming that there will be a delta t. We will still cut the unitary into smaller delta t's because that's where we get some optimality. So we will still use short time intervals. But anyway, we Taylor expand the exponential, and then we write the Hamiltonian in this PMR form, and we raise it to the power n, and we sum over n. And what we are trying to do now, or what I'm trying to show you, is to see what happens when we act with this unitary on a computational basis state. Before I do the action, once we write this thing and expand the parentheses here, what you need to, I guess, hopefully see, or what you see, is that when we expand this thing here, we end up with a sum over all possible products of length n for every n, of length n of either d0 or dj pj, because we're just expanding this. So once you do that, you have a linear, essentially all the products. And there are many of them. There are exponentially many of them. But I'm not going to worry about it because we have a quantum computer. We'll do everything in superposition. But there are many of them. What I did want to show you is that if I take one term, this is one random term that I chose. This is, for example, one out of many, many terms that appear in the sum. And I want to ask myself what happens when I apply this, I act with this term on a basis state, okay? And let's see what happens. So when this term acts on a basis state, when the d0 acts on a basis state, I can just pull out a number, right? Because it's a diagonal. Diagonal times basis state is just a constant. And then comes this p2. The p2 acts on the basis state, but it just permutes it to some z prime, right? But then when the d2 comes and acts on the z prime, it's a diagonal. So I can pull out another constant. And then comes another d0 that acts on z prime, but it's diagonal acting on z prime. It gives us another, in this case, we have two d0s, or here, two d0s. So it actually gives us this a matrix element, diagonal matrix element, which I call E squared. And then comes this P1. P1 is a permutation. When it acts on a Z prime, it permutes it to some Z double prime, and so on. So what happens is that all the Ds, the P's stay put. They just permute the Z's. But the D's, we can take them out as constants, okay? And we are left with the P's, which I call the off-diagonal core of that particular term. The reason I call it the off-diagonal core, because there are many, in fact, there are many cores, there are many terms, in fact, that have the same core. Usually, or in general, the core will be just a product of P's, like I showed you in the example. But there are many, many terms, actually, that have the same P. For example, if I go back, you could have another term with d0 to the 4, and here, instead of two d0s, maybe I'll have just one. They will have a different constant, but the same core, okay? And if we look at a single core, and you can imagine, or that's what I like to do, is imagine that this core of product of P's that appear in the Hamiltonian, remind you, what they do, they just essentially take you from one Z to another, to another, to another. So they produce what we call a walk on the graph of basis states. So that's just a nice, for me, way to think about what this product of p's does on this basis state z, okay? So you can imagine each term as a walk on the graph of basis states. And in fact, the E's, the energies, the E of Z that I wrote, are actually, we have E of this guy and E of this guy, the diagonal energy of this Z, the diagonal energy of this Z. Essentially, the walk induces diagonal energies for every node that is visited. And it's also, there is those D's that are attached to the P's, and for every edge, which is just the jump, it generates another constant. So we have energies that belong to the nodes and off-diagonal elements that belong to the edges for every walk, okay? Thank you. Now, and this is, I think, the most important slide in some sense of this work, is because what we can do is we can take we focus on one off-diagonal core, P1, P2, P1, P3, for example. And we can look at all the terms that have the same core, and each of them contributes a constant. And I can sum up all these constants, and it looks like a very nasty sum, but the amazing thing that was very, I don't know, surprising, was that this whole sum, very complicated sum, turns out to be something that is called the divided difference, which I know that, again, I didn't know that before I saw it, so probably it's new to many of you. It's a kind of a divided difference of this function e to the minus I delta t with inputs, which are the energies that we visited along the walk of the off-diagonal core. What does it mean, the divided difference of this function with respect to these energies? The most important, I want to spend 2 minutes to talk about it, but the most important thing that I want you to know about this, the fact that we can write this entire sum as a very compact form, is that it's very efficiently calculable. That's the most important thing. It just means that I can take many, many terms, and I can calculate a single constant for all of them in one fell swoop. Now, what is divided differences exactly? It's a function that takes several inputs, not a single input, but several inputs. So I'll really make a very quick kind of digression to talk about divided differences. Essentially, when we talk about divided differences, you know what? Oh, yes.
I'm wondering that in your algorithm, in which step we need to use a quantum computer. So it seems that up to now all of these calculations can be done classically.
It's true that they can be done classically, but we have, if you remember, I'll go back a little bit. And so it's true for a single sum, I can do it classically. But the number of terms here is exponential. So I don't want to do it classically. I want to do it in superposition. I can do it classically, but it will take me like 1,000,000 years, right? But I want to do it in superposition.
Okay? And you have some algorithm to do it in the superposition way.
Yes, hopefully I'll get to that. Yes, absolutely. So, okay. So I'll just tell you a little bit. Maybe I'll skip because I don't have much time, but oops. I'll go here. So the divided difference of any function with respect to a number of inputs is actually, if all the inputs are very different, it's essentially the sum over the function at each of these nodes and divided by the product of all the differences between that node and the other ones. Again, what it means, maybe it will be easier to explain what it means. For example, if it is a single input, then it's just the value of the function at the input. if we have two inputs, it's just f of x1 minus f of x naught divided by x1 minus x naught. So you can think of it as a numerical derivative of sorts, okay? It's kind of a derivative of a point somewhere between x0 and x1. And when you go to higher terms, then f of x0, 1, and 2, it's f of x0, 1 minus f of x1 and 2 divided by x0 minus x2. It's like take the numerical derivative of the first two, the second two, and take the derivative of those. So it's kind of an endpoint numerical derivative, and by using some recursion, you can calculate this efficiently. Let's not go into that too much, just because we don't have time. I do have 13 more minutes, right? Because you're asking question, hopefully. Okay. And of course, feel free to interrupt, but I do want the 13, yes?
Hey, Itay. Wait, so I'm realizing maybe I didn't understand the notation from a few slides before. On the divided differences slide. The slide you said was mostly
this one, maybe?
Yeah.
Okay.
So, yeah. Could you just explain the notation there?
Sure. It's actually, this is a slightly abusive notation, but what it means is that if we had two inputs, say E0 and E1, and I'm writing e to the minus I delta t, it just means that it's e minus I delta t E0 minus e minus I delta t E1 divided by E0 minus E1. That's what it means, okay? And even if E0 and E1 are the same, actually, if you take the limit, I'll just tell you, it's still very well defined. It actually becomes the derivative itself. So again, I spent really like a few years, honestly, studying divided differences, but I will, this is what it means. It's just a numerical derivative on that function, okay?
Is there a simple way to see why that top line is that divided difference?
No, the answer is no. There is no, it's a few pages of proof. So there is no simple way for me to see. But this is that, okay? I couldn't find a simple way to see that, but we can prove that. Okay, I'm going to skip the divided differences. There's so much to tell, but I'll skip them.
But that is like kind of the crux. That's what you exploit.
Yeah, exactly. There are many wonderful identities of divided differences that allow us to calculate susceptibilities and integrate the Dyson integrals in time-dependent Hamiltonians. And they do fantastic work, essentially. The math is, they're amenable to a lot of integrals and stuff like that. And so honestly, for me, the interesting thing are all the properties that we proved about divided differences, which I will skip because I want to show you the algorithm itself, okay? All right. So I just told you what happens, or like the idea of writing e to the minus I delta th and acting on a basis state. And this is just taking the operator and acting on a basis state. It doesn't tell us what the quantum simulation algorithm is, and which is what will come next. So just imagine that we were able, for every core, every product of p's, we essentially we sum up all the terms that have the same core. So we end up summing over all the cores. What is this? It means that we're summing over no permutations and then all the single permutations, P1, P2, P3, however many appear in the Hamiltonian, and then all the pairs, P1, P2, P2, P3, P1, P1, and so on, because we have to sum over all the cores. This is this sum. Each summoned is a product of p's. This constant comes from those d's that are also constants that come with the edges, if you remember. And this is the divided difference that comes from the diagonal part of the Hamiltonian. The E's are the matrix elements of the D0 part, if you remember. So essentially, we have this thing here, that if I act with a short time evolution on a basis state, I need to sum over all the walks, essentially, on the Hamiltonian graph. And each walk gives us a simple permutation. It's a simple permutation because, remember, the permutations are Pauli x's. So it's just a product of Pauli x's, which is just a Pauli x. It's a C-naught, essentially. And this thing here that I try to convince you, it's a constant, and I try to convince you that it's efficiently calculable. So hopefully it starts to remind you a linear combination of unitaries, because these are constants that are efficiently calculable, and these are unitaries, which are p's, product of x's, which are unitaries. And so we are hopefully starting to see what we can do with this guy here. So I'll just say again, if we go back to e to the minus I h delta t, we write it as before, as with Trotterization, as with LCU. We write it as a product of short time evolutions. But the trick is, and this is maybe important that I kind of skipped, is that the permutations that appear here, they don't include P0. And this means something. And what it means that when we, I guess the norm in some sense, if you remember, the delta t's depend on the norm of the Hamiltonian. For those of you who do Hamiltonian simulation and slice the Hamiltonian or slice the time to short time evolutions, usually the dimensionless time depends on the actual time, but it also depends on the norm of the Hamiltonian. Usually, the product of time and the norm of the entire Hamiltonian set the tone of what the complexity is. But in our case, because we don't have the D0, in fact, we only need to multiply t, so the dimensionless time is actually t times the off-diagonal norm of the Hamiltonian, which in many cases is much smaller than it's always smaller, but sometimes it's much smaller than the total norm of the Hamiltonian. You can think of a Hamiltonian with a very big diagonal norm and a smaller off-diagonal. And so the diagonal part is actually integrated out. It only appears in these divided differences, which what I will show you right now is that the divided differences, we can write them as a sum of phases. I'll get to that actually right now. But what I'm trying to say here is that we do take short time intervals, but relative to other methods, because we don't only care about the norm of the off-diagonal part, then our short time intervals are much longer than other methods because of that, and therefore the number of repetitions is much smaller, inversely smaller. I have 5 minutes, right?
Yeah,
Good.
I'm going to stand here to make you...
Okay, Good. You're a very good chair. Okay, so I guess maybe I'll skip to the good stuff, at least for me. What we showed is that I'm just rearranging, I guess, the unitaries that we found. They are, again, a product of p's. And this is just a rearrangement. And we just wrote, I guess, the divided difference part as a sum of what I would call a diagonal non-unitary. Essentially, it means that if I write the entire, okay, what I showed you is the action of e to the minus IH delta t on a z, but I can turn it into a unitary, and we have the p's from before, and for the divided differences, what we end up with a non-diagonal unitaries, because this is actually, in fact, it's not a real phase. This thing here looks like a phase, or at least when I write it like that, you may think that it's just a phase, but it's not. Even though it is not a phase, what we showed in our work is that we can take any divided difference that looks like that, and we can apply, this is one of those properties of divided differences that actually Leibniz, Newton invented the divided differences, and Leibniz came and he showed that you can actually replace a divided difference with a time interval t into a sum of shorter time intervals of divided differences. So you can take a divided difference and write it as a sum of smaller period time divided differences. It looks like that. Psi could be 1/2, for example. And you can keep slicing and keep adding terms, so you can end up with a very large sum of replacing e to the minus I tau or delta t into a very long sum of products of divided differences with very short times. And it turns out that if the times are short enough, you can actually replace each of them with an actual phase. So if t is small enough, these are actually phases. And to get to the very bottom of what I was trying to say is that if you are adding another sum over all the divided differences, you can end up with a diagonal unitaries, meaning just essentially sum over real phases times z. So for every zz, you have one phase. So this is an actual unitary with a phase. So because I don't have a lot of time, I will just tell you that essentially the controlled unit, this is a linear combination of unitaries because this is a constant, this is an actual unitary because it's a product of C naughts, these are the P's, and a diagonal phase. And each of them is very simple. C naught, very simple. Its product of x's is a C naught, it's very simple. And this is a diagonal phase unitary, which is also very simple. So the point I wanted to talk to you about LCU and stuff, I'll skip all of that. The point is that we end up with an algorithm that only has C naughts and diagonal phases. And if you do the math properly, it scales as the other LCU Taylor expanded algorithm. So it has optimal scaling, and it's also simple to implement. And it has certain, I have 1 more minute, it has certain advantages over existing algorithms. The fact, again, that we can integrate, we don't pay for diagonal components. The number of terms in the LCU is considerably, even O of n, sometimes O of n squared, smaller, so less ancilla qubits. And if we do the same thing for time-dependent Hamiltonians, then we can show that we don't pay for oscillations. And of course, I didn't talk about any of that, but if you believe me, also the cost is linear in evolution time. So I invite you to read the paper and talk to me about it. And hopefully, maybe we can get some of you to implement those algorithms on actual devices. So thank you very much. I'll stop here.
We will have 2 questions and then break.